we present Interpolated SelectionConv, a method for transferring 2D convolution weights to networks that operate on spherical images and surfaces. Convolutional neural networks allow for extraordinary capabilities when working with traditional 2D images. However, what do we do if we want to bring those same capabilities to spherical images? Using deep learning techniques on spherical images is a well-explored problem, and research in this area generally falls into two categories. The first is surface-based methods. These techniques use convolution operations that are specifically designed for spherical data, working on that 3D data directly to minimize the amount of distortion, but require large spherical image datasets, which can be difficult to create. The second category of techniques is projection-based, where the aim is to take what has been learned in traditional 2D domains and transfer it over to the spherical. This is done by using deformed convolutions or special projections of the sphere. These methods, however, often still require fine-tuning within the spherical domain and are limited by the nature of their fixed representations. The aim of our work is to begin to bridge the gap between these two approaches to spherical images by operating directly on 3D data like the surface-based approaches, but allowing for transfer from 2D networks like the projection-based approaches. To do so, we build from our previous work, SelectionConv, which is a technique that brings 2D convolution weights into graph structures. This is done by pre-processing a graph into multiple adjacency matrices, each one representing a different cardinal or ordinal direction. Thus, each direction can be assigned specific weights, which can be pulled directly from convolution networks trained on 2D images. This gives a framework by which we can operate on images with optimized weights, but have the flexibility of a graph structure. In our original SelectionConv work, we always assumed that the nodes in the graph were aligned to the 8 cardinal or ordinal directions, since our experiments primarily showed the ability to operate across seams and unique image types. However, such an assumption means that SelectionConv performs poorly when nodes do not lie along such axes, which would commonly be the case in general point cloud structures. To fix this, we present Interpolated SelectionConv, which modifies the original technique by allowing for fractional values in the selection matrices to interpolate between neighboring weights. Determining these interpolation values become part of the preprocessing step and can be calculated using angle-based or barycentric techniques. For example, in our original SelectionConv work, we operate on spherical images by making a continuous graph from a cube map image. This graph could properly connect across seams of the cube map, as well as account for the proper up direction in each region. However, the cube map projection still has distortion, and our approach required a high resolution to properly represent the sphere. In comparison, our new technique does not operate from a projection, but can sample points that are equidistant from each other in 3D space, and then can build the graph directly on the surface, using the interpolation to properly account for the direction of each local edge to a node. This lowers the amount of distortion in the convolution, while simultaneously providing the flexibility to use any sampling resolution or technique. We demonstrate the effectiveness of our method in the following experiments. First, we demonstrate the ability to create high-quality style transfer images in the spherical domain. In comparison to previous approaches, Interpolated SelectionConv is visually comparable, while using less points overall and avoiding seams and artifacts in the polar regions of the sphere. Additionally, we show the results of using our approach for the task of spherical segmentation. We evaluate on the Stanford 2D 3DS dataset and have state-of-the-art results for directly transferring weights from networks trained on 2D planar images without performing any additional fine-tuning. Lastly, our approach is general and flexible enough that it can operate on any surface, not just spherical images, as illustrated by our ability to perform style transfer on this 3D model of a bird. Texture maps for 3D models usually have many 2D discontinuities and scale differences among regions that should be contiguous in 3D space. With our approach, we can operate directly in the 3D space and even choose the level of detail we wish to sample from the 3D model when we perform the convolution. Check out our paper to learn more. Thank you.